Okay, in the previous two sessions, we have reviewed the remarks about the uniform interpretability, and then what did we do? In the second session, we stated and improved the theorem about the monotone class, the monotone class theorem for functions, and then we started introducing the definition of filtration, and we rephrased the notion of independence in terms of filtrations. So let's review briefly this thing here. We say that a collection of sub-sigma algebras of H forms an independency if the expectation of random variables v1 times vn can be factorized into the product of the individual expectations, where v1, vn are random variables measurable with respect to each filtration. And then we saw two propositions. Again, we have a sequence of sub-sigma algebras of H for y less than n. We have that the sigma algebra generated by a collection Ci forming Fi. So consider Ci such that I'm very bad at writing script letters. Such that Ci, consider Ci such that the sigma algebra generated by it forms the sigma algebra. Then the collection of these sigma algebras is said to be an independency if and only if the probability of the intersection of events h1, hn can be factorized into the product of the individual probabilities for events hi in the collection Ci extended with the entire sample space. And my question here is, why do we extend this in this way? And then we saw that partitions of independencies are independencies. Let's continue now. Okay, so we have a proposition which can be rephrased in two alternative ways now. The first one is this: consider x1, xn random variables taking values respectively in the spaces ei or I from 1 to n. They are said to be independent if and only if the expectation of a function, right, if f1 composed with x1, if n composed with xn, can be expressed also in this way: the expectation of f1 applied to x1 expectation of fn composed with xn. And this is basically equivalent to this thing here. as far as I know. Okay, for any function f1 from f, for each function f1 fn, and for each x which is measurable with respect to I, e1, en. And the second alternative way is this one. Again, consider x1, xn, blah blah blah. Then they form an independency if and only if the adjoint distribution equals the product of the marginals. It's the product of the marginals. Let's put it like this. Let me see if the music. Okay. Music is not working. Let's put like this. Okay. So a collection of random variables forms an independence if the joint distribution can be written. The joint distribution of this collection can be expressed as the product of the marginal distributions of the individual random variables. And here, well, we have a remark that they are basically the same thing. Why? What is the link between these two? We should recall, I think, mu f, expectation of x, the link between the expectation and the distribution of x. The expectation of x is the same as integrating a function with the distribution of x as a measure, if I remember well. And so here we should have this, while here with this should be this, something like this. Or it was expectation of f applied x. Let me check. I can find it. Okay, this theorem, yes, expectation of f applied to x is the same as integrating the function with the distribution of x. Okay. And here we have proof of one. So we have to prove that the expectation of v1 vn can be factorized. And here it's this for any v1 vn. And which is positive and measurable with respect to sigma x1, sigma xn. But we know this holds because of theorem delta, which was the one about the measurability of functions of our unknown variable. Still not completely clear to me, at least. But let's keep going. The proof of B here it says that from a proposition that we have previously seen, the first expectation written in integral form is pi of dx1 dxn f1 fn f1 of x1 fn of xn and this is integrated over the Cartesian product. And because of the proposition, this is the integral over e1 mu dx1 f1 x1 integral over e2 mu 2, no, simply mu dx2 f2 x2 and so on. Where pi is the joint distribution of the vector, and considering the positivity of functions, we have that the product measure factorizes in this way, basically. So yeah, here it would be better to write mu1, mu2, mu1. So this is the proof of this thing, and this step. Okay. This is related to this maybe in such a way that the expectation of a random variable is a function of a random variable. Because it's the integral, and the integral of a function is a function, actually. Is this a correct interpretation? I don't know. We open a new paragraph to talk about some of random variables. So consider x and y with distributions mu and nu respectively. And we want to find the distribution of x plus y. This is given by the following formula, which is the convolution of the two measures the integral of f using as measure the convolution of the two measures. Cool. Which is the expectation of f. Expectation of the function of f. Of a function of f. Mamma mia. The expectation of a function of x plus y. More explicitly, the integral over r mu dx, integral over r nu dy f of x plus y. And to see why, let us choose as function the indicator on the interval minus infinity z, with z included. So that the expectation of f of x plus y is the expectation, well, okay, is the expectation of this indicator applied to x plus y. And this is nothing but the CDF x plus y less than z. Here it's a small case z. Which explicitly is the integral over r mu dx, integral over r nu dy times the function. Here it's x plus y again. Here it says that the right hand side can be further worked out in the following way. So we can split it basically. What does it mean? What are we doing here? We want to find the distribution of a sum of random variables, and to do that we consider this strange thing. Here I understand basically nothing. I mean, what is the point of all of this? What are we doing here? I mean, the final result is that we integrate the CDF of x on some point z minus y with the marginal distribution of y. We get the sum of the distribution of the sum of them. Ok, se lo dici te. Here we have an example which I still don't understand. Consider x absolutely continuous with density h of x. Then probability that x plus y is less than some value z is the integral over r, the distribution of x z minus y nu dy, which is what we derived before. So in this case it's the integral over r nu dy and the integral from minus infinity to z minus y of h of x, h of t dt. And making the following change, letting w be t plus y, this becomes integral over r nu dy integral over from minus infinity from minus infinity to z of h of w plus y dw. Everything is negative, so you can exchange the integral and we get this. And this thing here is the density of x plus y. And if y is absolutely continuous, this becomes the integral over r h of w minus y nu dy. No, g of y dy. Again, what does it mean? I don't know. I should. It would be nice to have an example or a problem involving a concrete computation to see how it really works. Okay, well, we now switch, or it would probably be nice to see it next time and have lunch, which is a quite nice idea. So what did we see now? We saw, again, independency rephrased in terms of sigma algebras, and this strange derivation of this distribution of the sum of two random variables. Okay, so next time we will talk about the sigma algebras, which are used in the Kolmogorov-01 law theorem. And after that, we will begin a whole new chapter on convergence. That's it.